Okay, so hi everyone, my name is Krzysztof Leśniak and I would like to give introduction to Ocaml programming language. But first I would like to steal the quote that I'm not an expert, I'm just a dude. I'm not an expert on functional programming and not an expert on Ocaml. I just played with it a little and like it and would like to share some of its features. So what is Ocaml? On the official website of the language we can read that Ocaml is a general purpose programming language with an emphasis on expressiveness and safety. And some of its features. This is a statically typed language with support of type inference. So this means that once we introduce a variable, its type cannot change. But thanks to type inference, we usually don't have to specify the type of a variable. In pretty much most of the cases, the type can be inferred by the compiler based on the usage of this variable. We also have automatic memory management, so we don't have to deal with memory manually. There's no functions like malloc or new to allocate memory. Memory is automatically allocated when we introduce new variable, and similarly there's no functions like free or delete. The memory is automatically freed by the garbage collection system. Ocaml has built-in REPL support, so this is read eval print loop. So instead of putting all the code in the file and launching compiler, we can start interactive mode, and in this mode interpreter reads expressions from standard input, evaluates them as Ocaml code, and prints the result on standard output. There is also a pretty efficient native code compiler, so if we need some more performance, we can compile the Ocaml code to machine code, and it is pretty efficient for a functional programming language. Of course, code written in, for example, C or C++ still would be faster, but it's pretty good for a functional programming language. So Ocaml is a safe language because of its static typing and automatic memory management. We cannot corrupt memory in any way. We cannot dereference null pointer, and we don't have to deal with lifetime of objects because this is automatically handled by the compiler and garbage collection. Ocaml is functional programming language, but it's not pure, so it supports also some imperative features like mutable variables or for loop, mainly because some algorithms cannot be expressed in an efficient way, in a pure functional way. So this is why it supports also imperative code. Supports also object-oriented capabilities and also exceptions. So let's take a look at some simple code samples of Ocaml, and let's start with looking at how type inference works. So in these samples, when you see a code that follows a hash sign, this means that the code was interpreted by the REPL in the interactive mode, and what's below is what the interactive mode output as a result of evaluating this code. Notice also that there are double semicolon at the end. This is required in the interactive mode to mark the end of an expression you want to evaluate, but it is not required in code we write in the file. So here we're defining a variable and assigning it value 1. This is done using the let keyword. This is kind of similar to defining a variable in imperative programming languages, but here the value once introduced cannot change later. And we see that the type was inferred to be integer. And similarly, if you want to assign a floating point value, for example 1.1 to a variable, the type is inferred to be float. And similar for strings, the type is inferred to be a string. We can also define functions. We can use the fun keyword for that. And in this case, we have a function taking single argument x, and it produces x plus 2 as a result. And in this case, this is an anonymous function. And here we see the type signature of this function. This means that this function takes integer as an input, and it produces integer as an output. We also can have functions that takes more arguments. In this case, this function takes two arguments x and y, and produces x plus y as a result. The type signature in this case is a little bit more complicated, but it basically means that it takes two integers as input and produces integer as output. I will explain it a little bit more later. So the fun keyword creates an anonymous function, so we can use the let keyword to assign this function created by fun to variable, so that this function has a name, and we can then refer to that function using the name. So here we're creating add function with two arguments, and it just adds the arguments, and it's the result of the function. There's also a shorter syntax for this, for creating functions, also using let keyword. In this case, we use the let keyword, then the name of the function, and then name of the arguments, equals sign, and the body of the function. And this is exactly the same function. The type signature is also the same. And we can call this function via this name add, provided two arguments as parameters, for example 3 and 5, and we get expected output 8. Notice that there are no parentheses around the arguments. If we separate arguments from the name of the function with just a space. And here's some more complicated example where each of the argument to the add functions is itself a result of evaluation of another function. And we see that the parentheses are used to group statements rather than surround the arguments. So in this case, the first argument to add function is result of applying the add function to parameter 1 and 2. And second argument is the result of evaluating this function for arguments 3 and 4. So let's take a look at this type signature generated by compiler, this int arrow int arrow int. This means that it takes two integers as input and produce one integer as an output. But this pretty much looks like it's two functions actually, and we can rewrite this function in another form. So in this case, this function add takes only one argument, x, and as a result it returns another function that also takes one argument, and this function returns the sum of these two arguments. So this is why the signature looks like this, because the add function takes single integer as an input, and it produces another function that also takes single integer as input and produces integer as output. And this is known as carrying, and this is carried form of the function add. And what this gives us is the ability to partially apply the function to arguments. So our add function takes two arguments. So in imperative language, if we want to pass only one argument, this would be a compilation error. But in this case, if we pass a single argument to this function, we will get another function that takes integer as input and integer as output. In this case, this add2 function will just add 2 to the parameter. So if we call it with, for example, value 5, we get output 7. We can also define recursive functions. This is done using the special let rec notation. And this is a function that just calls itself. And in this case, we have a function calculating the factorial. And it calls itself while the argument is greater than 0. And here is somewhat more complicated example. We also can have mutually recursive functions. So these are the functions that calls each other in a recursive way. This is also done using the let rec keyword. But we have to define all of these functions in a single expression and combine them with keyword AND. And this is an example of functions isEven and isOdd that checks whether the given argument is even or it's odd. This is pretty artificial example, but just to illustrate the point. We can also have custom operators, and this is also done using the let keyword. It is very similar to creating a function, but instead of name of the function, we provide the symbol of the operator. This symbol can contain multiple characters, but it's not like we can provide any character we want. There's just a few possible characters we can use, and we have to surround this symbol in a parenthesis. So in this example, we create an operator plus plus that takes two arguments and calculates its sum multiplied by 2. So when we call this operator with values 2 and 3, we will get value 10. And custom operators lets you create code that is more expressive, but on the other hand, it can be a bit hard to understand if there's many new operators introduced. So this is an example of code I have written using external library. This library is for creating parser combinators, and it heavily uses custom operators. So what this code basically does is this is used to parse variable name followed by double equal sign and then some string literal. So we have this parser var name, and it parses the variable name, and here we have a custom operator provided by this library. This name of the variable that is matched by this parser is passed to this function, and here is another operator from this library. This combines two path sets and returns the value of the right hand side path set, and then we have yet another operator, and the result of this expression is piped via this function. So if you're not familiar with what these operators do, then this code might be really hard to understand, but on the other hand, it can be really short and expressive if you do know these operators. So Ocaml also supports pattern matching, which is like an if statement in imperative programming language, but is more expressive and is more powerful. This is introduced using the match with keyword, and then a set of pattern follows, and each pattern consists of this pipe character, then an expression we want to match, then arrow, and the code that will be executed when the pattern expression will be matched. only one such code block will be executed in this match expression. And each pattern will be tried to be matched. First will be tried the first pattern, then if this will not match, the second pattern will be tried, and if not, the third pattern will be tried. And here we have again factorial function, but implemented using the pattern matching. So in first pattern we check if the input argument is equals to 0, and if so, the function returns the value 1. In another pattern we check if n is equals 1, and if it is, then we also return 1. And the third pattern is a bit different because it doesn't check for specific value, but instead it introduces variable k, and we didn't have variable k introduced earlier, so this variable will be created here and will always be equals to n. So if neither of these two patterns match, the third pattern will always match, and will call this function recursively with argument decreased by 1. And there's shorter syntax for pattern matching. So if we have function that is doing pattern matching on its first argument, like we have in this factorial function, we can use the function keyword. And in this case, the variable name, we don't provide the name for this variable, but it is automatically matched against the patterns we provide. So these two functions are equivalent. And we can match not only on simple values, we can also match on more complicated structures. Pattern matching is often used to match on lists. So in this case we have a function sum that accepts a list as input and produces sum of its elements. And in the first pattern we match an empty list, and in that case we return value 0. And the second pattern is a bit more complicated. It uses this double colon operator. This is basically a constructor for lists. So an empty list will be matched by this first pattern, the empty brackets. And here we are matching non-empty list. So here we have head of the list. This is the first element of the list. And then we have the tail of the list, which is all the elements of the list except for the first element. And then we call this function recursively for the tail, and again it is matched against these patterns until all the elements are matched in this way. So let's take a look at some simple calculations. Let's say we want to calculate sum of 3 integers, and we use the plus operator for that, and it results in the value 6. But let's say we want to calculate sum of 2 floating point values, and we also use the plus operator for that. But this actually results in a compilation error because Ocaml expected a type integer here, and we provided float. So this is because the plus operator operates only on integers, so it accepts 2 integers and produces an integer as an output. And for floating points we have a separate operator, plus dot, and this operator is used to add floating point values. And if we call this operator using floating points values, then we get the proper result. Okay, but let's say we want to add integer to a float. So we cannot use the plus operator, but we also cannot use the plus dot operator because we would get a compilation error. So there's special conversion functions for that, because we need to be explicit what we want, whether we want to convert integer to float or float to integer. And for example, we have function float of int that accepts an integer and outputs a float as a result. So we can use that function to convert integer to float, and then use the plus dot operator to produce the sum of 2 floating point values. And let's say we want to do some string formatting. Let's say we have some variable of integer type that we want to embed in some kind of message to the user. This is similar to the case when we want to add integer to a float. We also need to use conversion function to convert integer to string, and then we can use the special circumflex operator to join two strings. And this works fine for such simple cases, but if we have, for example, more values that we want to embed in a string, this can be quite complex and verbose. So there's a sprint function for this. It works basically like the sprint function from C language. It accepts a format string that has some format specifiers. This is this %d, and then a set of values. So for each format specifier, we need to provide a value that matches the type of this specifier. So %d tells us that it accepts an integer. And using this sprint function, we can more easily embed some values in a string. Here we have an example of integer, floating point, and string. And in C we have this issue with sprint function, that we need to make sure that the type specifier matches the actual type of value we provide, because otherwise bad things can happen, because in C we cannot like check it at compile time. But here it is actually checked at compile time. So if we provide a type specifier that accepts integer, but we provide a floating point value, like in this case, we would get a compilation error. And this also means that the format string needs to be a compile time constant. So similar to sprint functions, there is also printf that works basically the same, but instead of returning the formatted string, it prints the string on standard output. And similar to sprint function, this is also type checked at compilation time. So this will also result in an error. And we also have scanf function. This works a bit different because it accepts a format specifier, format string, and then a function that takes argument for each type specifier we put in the string. So in this case we usually need a single string, so we need to provide function that accepts a single value, which will be a string. And we can read also multiple values, so in this case we read 2 strings from standard input. So Ocaml also supports some imperative features, and here we have an example of function calculating factorial in imperative way. So to calculate factorial in this way, we need to have a for loop and mutable variable. So we introduce for loop with a for keyword. This is, I think, pretty straightforward. Mutable variables are a bit more complicated. We create a variable that we can mutate using this ref constructor, and this creates a reference object that we can later mutate. And to get current value in this reference object, we need to use operator exclamation mark, and to assign a new value to this object, there's also separate operator colon equals. So if we call this function with value 6, we get 720. Ocaml also supports variants. So, for example, we can create a list of integers. We can create a list with brackets and separates the elements with semicolons. So in this case we have a list of integers, but let's say we want to create a list of integers and strings. So this won't work because all the elements of the list need to have the same type. So we will get compilation error. But what we can do is we can create a variant type, which is either an int or a string. So this uppercase int and string is called constructor of this type, and each of them accepts a single value. So using this new type, we can actually create a list that contains both integers and strings, but they are wrapped in this variant type. There's also recursive variants. So this is a type that in one of its alternatives holds the type we are creating. So a binary tree would be an example here. A binary tree is either a leaf holding an integer, or it's another tree holding two another trees. And we can use these leaf and tree constructors to create a binary tree, and in this example there's a tree holding two leaves with values 1 and 2. But here we have this integer hard-coded in the leaf, so in leaf we can only have integers. So let's say we want to create trees not only holding integers, but maybe some tree holding strings, or tree holding floating points, or any other type. So we can use parametrized variants for that. And this looks pretty much the same like the previous example, but we have this type annotation, which is the actual type stored in the leaf. So we can actually call it with the same way like we called the previous tree, and we see that the type inferred by the Ocaml compiler is int binary tree, which means that this apostrophe a will be an integer, so leaves will hold an integer value. But we can also create leaves that holds strings. So here we can see that type inferred by compiler is a string binary tree. So this apostrophe a is now string. So here we have an example of the factorial function using the pattern matching. but this is pretty inefficient because it doesn't use the tail call optimization, because after calling itself we have to multiply the result of this function with this n. So what we can do is we can introduce an inner function and this function will be implemented in a way that it is tail call optimizable. So this function is no longer recursive, but this inner function is, and this function accepts additional variable, and this will be an accumulator. This value will store the result of this factorial function, and we initially call this function with argument 1, and this will be our accumulator, and the argument we want to calculate factorial, and then for each invocation we increase the accumulator by the current argument and calls this function recursively with this value decreased by 1. And this will be called recursively until this function will be called with value 0 or 1, in which case it will just return the accumulator. And we can also add some checking to make sure that the function is called only with non-negative values, and applies an exception for values that are negative. Here's another example. This is a FIZZBUZZ. FIZZBUZZ is a program or a function that accepts a single integer and produces a string, and if the input value is divisible by 3, it should return fizz string. If the value is divisible by 5, it should return buzz string. But if the value is divisible by both 3 and 5, it should print FIZZBUZZ string. And in any other case, it should just print the integer. So instead of a set of, for example, if statements, we can use the pattern matching, and we can calculate the modulo division by 3 and modulo division by 5, and use pattern matching on both these values to check both of them at once. So first we check if the input value is divisible by both 3 and 5, and for this case we return FIZZBUZZ string. And if this pattern won't match, then we check if the value is divisible by 5, for which we would return buzz string. And if it also won't match, we try checking if the value is divisible by 3, then we return fizz. and if none of this will match, we just convert the integer to string. And this underscore here is a special construct that is used to match any value. So for example, here we're saying that the second value needs to be 0, but the first one can be anything. Some tools that are commonly used in Ocaml. There is Ocaml, which is package management and switch management. If you need to use some third-party library with Ocaml, you can search and install these libraries. It is similar to Python's pip and Ruby's gems, and switch is somewhat similar to Python's virtual environments, which is a separate Ocaml environment with separate packages installed, and you can also have like separate Ocaml compiler in it. So you can have multiple switches and each of them can have its own version of compiler, which could be quite helpful. Dune is quite popular build system for Ocaml. So by default, Ocaml doesn't include any build system. All the build systems are like external libraries installed with Ocaml, but Dune is, I guess, currently the most popular one. There are also other build tools, so you can pick what you like. There's some transpilers to JavaScript. There is JS of Ocaml and a buckle script. Buckle script actually creates JavaScript that is very readable, because JS of Ocaml can generate a bit more complicated JavaScript code. There is Merlin, which provides some IDE features to the text editors. It supports Vim, Emacs, and some other editors. And there's Utop, which is really nice interactive mode for Ocaml. Default installation of Ocaml has an interactive mode, but it's pretty minimal, and Utop gives some more features like code suggestions and completion, and it works really nice. Some actual usages of the Ocaml. So Ocaml standard library is mostly written in Ocaml. There's a Haxe programming language, and its compiler is written in Ocaml. Haxe looks a bit like Java, that can be transpiled to C++, Java, JavaScript, and I think quite a few more languages. So there's a cog tool, which is a tool for formal verifications. It is written in Ocaml. There is a mirage os, which is a library for creating unikernels. There is FFTW library, and while this library is implemented in C, the Ocaml was used to actually generate the C code. There is float, which is type checker for JavaScript, and there is similar tool type checker for Python, and there is also the trading company Jane Street, which uses Ocaml as their language of choice because it's expressive language and is pretty easy to learn. Some links. This is the official web page of the Ocaml language. Here are some nice PDF files with a nice overview just on a few pages. Provide some basic overview of the language. There's a really good book, Real World Ocaml. This is second edition of the book, if I recall correctly. It's really nice. It's really good. There's also Ocaml manual on INRIA pages. INRIA is French Institute for Research in Computer Science. It is main developer of Ocaml. There's also a page with 99 problems to be solved with Ocaml, and there's also solutions. I think it's pretty nice way to start playing with Ocaml because the initial problems are pretty easy to solve. There's Sketch, which is like interactive sketchbook for evaluating Ocaml code. So you can try Ocaml in your browser without installing it locally. And there's some link to benchmark of programming languages. This links to comparison of Ocaml with Haskell. There's also Ocaml compared with C++ and some other languages. And I would like to leave you with a quote that a language that doesn't affect the way you think about programming is not worth knowing. And I really think that functional languages can change the way we think about programming, so it's really good to know at least one of them. It doesn't have to be Ocaml. And that's basically it. That's everything I want to share today, so thanks for attention. Here's my link to Twitter. You can follow me if you like. There's a link to itch.io where I publish some small games for game jams I do, and I started writing some posts on Dev2. There's not much for now, but hopefully will be more. And if you have any questions or comments or, I don't know, suggestions, then I can try answering it now.
So does anyone has any questions to Chris? Okay, so maybe just one question from me, because you've mentioned Buckle script, right? And have you experimented with Buckle script at all? I mean, running any Ocaml code or generated by Buckle script code in the browser?
I just played with it a bit.
Okay.
Not done much, actually.
And have you touched ReasonML, for example?
No, not yet. For now, I want to focus on Ocaml.
Okay, cool. And one thing that I remember is that I think first Rust compiler was also written in Ocaml. So
yes.
Taking that under consideration, it seems that among the people who are responsible for creating new compiler, Ocaml is actually a kind of a first-class choice, I'd say, or something like that. I mean, it's popular for a reason, right?
Yeah, it's quite popular for implementing compilers and, I guess, dealing with languages.
Okay, so will you share the slides with us after the talk?
Sure, I will generate the PDF file.
Okay, cool. It could be even in the reveal.js because I think you've used that, right?
Yes.
Okay, so let's talk about it offline. So anybody would like to ask Chris about anything? Okay, so you actually have the contact to Chris in case you would like to get in touch. So thank you very much for the talk. Yeah, I hope we'll see each other next time, hopefully in a month or so.
Thank you.
So I guess that's everything, as there are no questions. So thank you for joining us, and if you would like to talk about anything functional programming related, just feel free to reach me, and yeah, we'll organize this kind of a webinar.
Yeah, and join the Slack group.
Yeah, sure, because you know there are not many very active members there. Let's put it that way.
Yeah, unfortunately.
Okay, so not to waste your time, thank you very much for joining, and see you next time.
Yeah, see you.